Okay, so in this lesson, alright, they'll be talking about mainly on how to choose the fibers, type of fibers and its properties, how can fibers be made into fabrics, alright, and then after that we'll talk about polymer, alright, and then its matrix, its properties, and then we discuss on what are the criteria to select a matrix. So all in all in this lesson, alright, we'll talk about only fibers and also the matrix. So this will give you why am I talking? So the summary is that from page 63 onwards all the way to the end, we'll be talking about mainly on these two things. Alright, the one that I've said, these two. Alright. And in this video we'll talk about how to choose the fibers. Alright, and we'll talk about some things about the reading materials. Alright, that's something in case in the theoretical one that you want to do, at least you know what are the theoretical stuff that you want to read it out. So I'll just summarize all that in this video. So alright, so just to recap again, to repeat again, is that how to choose the fibers. Alright, and therefore let's start. If you still remember, in the last video we actually talk about the finger looking stuff. Alright, so we actually can skip this already, we can go on to the next page. Alright, so the dispersed phase, if you remember, is the fibers. Alright, and there is fibers and there is particles. Alright, so dispersed phase is talking about the things inside the matrix. Alright, that enables good stiffness and strong, and makes the material strong. Alright, to a certain extent. Yeah. So, previously I did mention that fibers are ductile and then matrix are high strength. Alright, I don't know whether am I correct still, but reading this, alright, you have another understanding of fibers. Alright, most commonly have strong stiff fibers, while the matrix is a weaker and less stiff material. Okay, so the matrix helps to take in any damages from the outside to protect the stiff fibers. Alright, so the stiff fibers often are easily broken. Alright, and this is why the fibers over here is stated to be stiffest and strongest. Alright, so in the past I do mention that I believe I mentioned it wrongly. Alright, so this is the correct understanding for fibers. Alright, so fibers are stiffest and strongest, while particles are just particles. Alright, it's just to it's much smaller than fibers, but provide better strength. Alright, whiskers are actually so-called particles. Alright, so strong because they are virtually flaw free. Alright, so therefore, ding ding. Yeah, so particles over here, they say particles are particulate flakes and whiskers, and over here whiskers is under fiber. That's why I don't know why. Alright, so let's just treat whiskers as the best one of all. Okay, so because it is so small, the diameter is 1 micron, so it's like micrometer. Alright, so it's very 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 small, so therefore this is the thing. So I've talked so much, you just need to remember that fibers is stiffest and strongest materials. Okay, and then particles also have to exhibit the same thing, just that they are much smaller. Alright, and take note of anisotropy in the material. Is the anisotropy is saying that strength in only one direction. Alright, while isotropy is strength in same strength in all directions. Isotropy is different strength in different directions. Okay, and that's all it is. The rest you can read it up. Alright, so over here you can also read it up. Alright, it's quite straightforward. Alright, then in other sense that you have to memorize this because the test may ask you this type of questions. Alright, what are the variables that influence the properties of a fiber reinforced plastics? Alright, so in this case, the fiber itself, these are the things that are the criteria for the fibers that influence the properties of your matrix itself. Because the matrix itself, if you think about it, alright, the name itself, fiber reinforced plastics. The plastic itself is already plastic. There is nothing much we can do about it. Alright, so we can add in the fibers to reinforce the plastic, so the plastic will have certain properties. Alright, so this is why the fibers itself are the variables that is a major influence on the properties of the full fiber reinforced plastics. Alright, so I hope this is pretty clear. So I repeat again, the fibers is the major influence to the properties of your FRP. Alright, the fibers is the one. Alright, the plastics itself is just plastic, its own properties, and that's it. Alright, the fibers you can change, you can edit yourself, you can make funny things to the fibers to make the plastics whatever properties you want. Okay, so in order to do that, your fibers are, these are the criteria to choose your fibers. Okay, so on over here it says to read the page 19 to 22. Okay, so what I thought was is to go through what does this page talking about. Alright, so after reading for a while, what I thought was is that I will continue on with the next page. Alright, and then at the end of this one, or you can choose to exit this video, or you can continue to watch what I've just highlighted in this. At least you get a feel of what are the things in the text document. But anyway, yeah, so let's continue with this page first. Over here, this one is aluminum oxide. Alright, in other words, this material, they call it, you need to know is that this is a sapphire oxide, sapphire glass. Alright, if you were to search Google, alright, you'll get to see this thing. Alright, it's a sapphire, like, like a sapphire. But anyway, so it's high tensile strength and Young modulus. Alright, so just if you were to take a look, alright, this is the density. The lowest density, the lightest, is this one. Alright, and then the fiber diameter, Young modulus, you can just take a look. Alright, so over here, although this is the lightest, alright, and the smallest diameter, but its Young modulus is somewhat is lower than the viscous crystal. You see, so there is a few things that you want to take note of is how do you take the diagram and take a look. Alright, so this is tensile strength over here and things like that. So from this chart you're able to see the values, and then from these values then you can articulate between what type of materials you want. Alright, so same thing over here, this is carbon, this is silica, but silica, take note that there is E-glass. S or R are the same thing, so it's the glass, and if you were to go into more expensive one, they call it a quartz. Alright, and then aramid. Alright, and just take note, sapphire is a very expensive material and it takes in a lot of heat. Alright, so it's a good heat resistance material, so to speak. The next question to arise is, I also don't know, is that if you take a look in the aramid, this is lighter than the sapphire glass over here. Alright, then over here the diameter is actually much smaller than this one. Alright, so this is lighter. Alright, so this is good, thumbs up. Alright, and then this over here is comparatively is heavier, it's larger diameter, so therefore this is good because it's smaller. But so in this case, what I would say is that the sapphire glass, alright, is how do I say, it can be designed for a very small applications, alright, for a very small material, because it's of its fiber diameter, it is very small, so you can have a lot of fiber diameter to put it in. Alright, so the number of fibers being placed will determine the total amount of strength or tensile strength or the Young modulus. So in other words, although you have all these values, you have to substitute it into certain equations to apply. Alright, so it depends on the number of fibers being used. Alright, the diameter, how it depends on the space you have. Alright, if this thing is maybe 3 cm, alright, how many fibers can you fit inside? Alright, things like that. So you have to also articulate between how many fibers will determine how many what type of tensile strength you will have. So over here, I believe is one fiber you have Young modulus of this, one fiber you have tensile strength. So if you have 10 fibers altogether, then you'll increase the total strength, or there may be a certain other calculations to determine that. Alright, so altogether, these are the things that you may want to understand for this case. Alright, and therefore this is it for the fiber. If you want to know more about this page, alright, then I'll just continue now. Okay, otherwise you can just continue with the next video. Alright, So from page 19 to 22, these are the stuff, alright, and I will not confidently say that I fully understand everything, okay, but at least something. Okay, so the something is that you're talking about to design uh, some design guidelines for fibers reinforced plastics. Alright. So over here if you take a look, alright, maybe I should take my pen. So this is, if you think about it, I would believe these are all the stuff. So you have a certain concept feasibility study. So you have to think about whether is your concept really feasible to design. Or some, because if you think about it, the shapes, everything comes to matter. Alright, where if you were to go zoom in all over here, you have to know whether people are able to provide this amount of quantity and schedule. Alright, and are there available technologies out there to create your composites, things like that. I'll not go into details much, but these are the things that you may want to know. Then after knowing all this already, these are the steps, then you want to go into the design analysis. Alright, we'll talk about all the analysis, integrity, all the strength, material cost, everything. Then you finalize your design and etc etc. You can read yourself. Alright, so this is one design guideline. The next one I would see is this one. Alright, so you have to talk about the performance, um, your approach, things like that. Alright, engineering. So you take in practical approach versus engineering approach. Engineering approach is just a theoretical one, I would believe. Alright, but you also have to take a look on the manufacturing side, on the uh, transportations, distributions, things like that. So you have to see and compare, and then you will decide your material. Once you decide on material already, then you will know type of uh, then you have to compare the material, compare the properties, compare the processes, compare the cost. Then from there you can somewhat converge down into the choice that you want. Alright, so these are the materials, and the materials choose can be your fibers, can be your reinforced plastics. Alright, so or your matrix, sorry. Yeah, so yeah, when you design a certain material, you are focusing on the material composition, amount of fibers being used, orientation and things like that, as well as the product structural geometry. Or because some geometry is you have to keep things simple, but however sometimes when you're doing architectures, geometries can be a bit of a tedious stuff. So you have to ensure that when you design a certain like this type of curvature, or what type of composite do you use, alright, and then what type of manufacturing methods do you use and things like that. Alright, and in order to explain how well to design a certain structure, alright, this is where it goes, but it can be a bit boring, so if you, yeah, anyway. So for example, a shape must be considered for a house to stand up against a hurricane. Alright, so low pitch roof. Alright, so what is the low pitch roof is, I believe this is your house. Alright, you have, if you have this type of roof, then you'll be better, right? Because as the hurricane blows, alright, onto the rooftop, alright, this thing over here will be stable compared to like that. Alright, like that, the hurricane will actually sweep this top apart very easily. So having a low pitch roof is pretty so-called a better design. But aesthetically, the low pitch roof may not be a nice design to design a roof, right? If you want to design something like a higher roof, meaning something like that, you have to take in considerations of the the structure, or because over here there is a aerodynamic factors, alright, where a certain amount, because there is a interior pressure and an exterior pressure. So if over here is lower than here, I forget which one is lower, which one is higher, but either one of it is, if it's lower or higher pressure, it will actually lift off. Alright, the roof over here, alright, will actually lift off. In other words, if you have this type of roof over here, okay, so this over here is a, I think over here is a higher pressure, over here is a lower pressure. Alright, so over here with this combinations, this piece over here will actually fly out. Alright, because of the hurricane is fast velocity. So if you remember, fast velocity means low pressure. So this is why I say that over here is low pressure, inside is higher pressure. So with this, the inside pressure will actually try to push this roof out. So there will be a structural point join, alright, a join or in other words some cemented whatever thing that is to bring this roof together. But however, due to this thing, aerodynamic factors, or it could actually pull this whole roof out. Alright, so having a lower degree, alright, you can actually create a less difference in pressure. So over here, this pressure and this pressure, there is lesser difference in pressure. Alright, so it's very technical now in terms of aerospace thing, but at least something for you to venture into if you find it fairly useful. So if the roof is 30 degrees from horizontal, it tends to deflect the wind better, alright, than gable designs. So if you check it out for the gable designs, just check it out. Alright, the gable designs are higher roof. Alright, so these are all higher roof. As you can see, angles are very steep. Comparatively, if you to use a low pitch roof, okay, so yeah, you see it's relatively low pitch. Alright, so I'll not go into details because I also never studied this thing, but at least you get a feel of how the thing goes, right? Over here, what is trying to give you the understanding is that in terms of structural design, you have to take note of all these things that happens for a structural system. Okay, and over here, different shapes will increase different stiffness. For example, this shape over here, if you were to press in this thing, alright, most probably you'll crack all over here, right? Or I don't know, but it's easier to deflect. So if I were to look this thing in terms of side view, so side view is something like that. Alright, it's protruding out. Alright, it looks like top view, but something like that. Alright, it's something like that. Okay, so over here, if you were to press this thing, most probably this thing will actually go in this direction and break. Right, so it's breaking in this direction, as you can see, or it's going in this direction. So when you design this brick, alright, and you want it to break in this manner, alright, so yeah, I think that's all what they want to say. So if you have a certain more steeper curve like this, alright, then will it be easier or harder to break? Alright, and most probably I think it is less easier to break. Alright, and if you were to go in this shape, then it will be more and more less easier to break. And if you were to go into more this type of shapes, alright, then it is more stronger in the directions of breaking, things like that. My explanation sucks, I know, but at least you get a feel of the meaning. Alright, and the next things for your complex design, if you have a really complex curvature geometry house, this is your house and you want it to look like this, alright, one way is that it is convenient if you were to approximate to some simple idealized form, alright, like some panel, some simple this shape, and then you mix with another shape, and then you have a curvature like that. Alright, so you have this form, and then you cut a semicircle to fit it in. Alright, things like that. So you have a standard shapes, and then you fit in like Legos. Alright, so the best thing if you have is to have a Lego type of composite or design structure, such that it is easier to place it in. Alright, and you also have to take note of finite element analysis. Alright, where we talk about most probably you know already your structure. Alright, and yeah, these are the stuff that you may want to note. What other stuff is important? So now you're talking about equations. Alright, in engineering books there are a lot of equations. You have to know what type of equations you need to use, and if you use, you have to know whether does it fit your design. If it's not, you have to adjust to meet your product performance. Alright, so you have to rewrite your equation such that it is easier for you to, and you can review to ASTM terms. Alright, it's an organizations that develop and publish technical standards for materials, product, system, and services. Alright, so it's a international system that you want to check. Alright, so whenever you design, you have to also read up the ASTM guidelines, so you can choose the material from there, I think also. Okay, and take note of when you design a certain stuff, it's not that thick wall is always good, because thick wall itself can cause internal stresses. Alright, you may think that certain thin thin materials could have increased stress, but it depends on your rearrangement and things like that, how you cleverly design your stuff. Alright, so one interesting thing of cleverly design your stuff is to have the types like hollow channel, alright, T-shape, I-shape beams. If you remember, if you have a beam, alright, like this is a hollow one, and normally this is the beam that you want it to put inside your building, right? So you put it like that, so the force is always acting on here, so over here it won't break quite easily, right? So because over here, if you were to have this hollow, it is easier and have less material, but it is anisotropy, right? It has a strength in these two directions, right? And that's over here, if you were to take a lorry and then you bang onto this thing, that definitely this will break or things like that. But at least you get to know that it depends on how cleverly you design your material. So you will not waste material. If you were to have a not hollow one, or everything is filled, then you'll be more expensive and hard to transport your materials and things like that. So normally this type of things have to be considered also when you design your structure. Yeah lor. And then you also have to take note of mechanical impedance. Alright, mechanical impedance, I would think is vibration, I think. So let's search it out and see. Yeah, so it is a measure of how a structure resists motion. Alright, so most probably it's something that you want to look into, and it's something that we don't kind of venture into in our system of study. So you have to take a look on the resonance, because there is a concept of static, alright, static and dynamics. Alright, so you have to take note of all the things and to ensure that the impedance, the design are good enough. Yeah. And formabilities is whether can you form your shape, alright, whether is your design, your shape of your design can be formed or not, things like that. So it's talking about manufacturability and things like that. And stress and deformations, you have to analyze your stuff, and and you can just search this thing. This is the book that you want, or if you want to continue to read it up, because I quite lazy already, but at least you get a feel of what type of things they are trying to talk about. And another thing is what I forget already lah. Over here it talks about a bending resistance, alright, and with shell structures, materials can be either single or double for fabricating purposes. So I actually you can search for single curve, double curve shell, and you'll see shell structure advanced building construction, alright, where you talk about advanced building, like sounds like I'm learning civil engineering now, things like that. So you can just take a look on the single and the double curvature, alright, the dome and things like that. So I'll not go into details, but at least something for you to venture if you need in the future. Alright, and what type of stuff do I need? You also have to take note of the certain temperature range for your product. Alright, what type of temperature range can it encounter? Like if you're designing a building for Singapore, you don't design something like snowing, right? So because there's no snow, but yeah, anyway, so and unfortunately computational analysis for us, normally we use ANSYS wherever is good, but however if you think about it, sometimes the computational analysis aren't quite well designed, so you have to try to, and this computation this computational analysis, alright, actually caused the designer to avoid understanding the real nature of the problem. So they thought that computational analysis is good enough, but they didn't actually analyze the real nature of the problem, what type of wind is it coming in and things like that. So it is really advisable if they could come out a theoretical system on themselves and compare it with the computational one, and by using the computational one, you can alter how you want to design your stuff, and you can check carefully with the logic and reasons of what type of problem are you encountering, and using this particular problem, once you fully understand the problem, then you will use the computational analysis instead of straight away use the computational analysis and see what is the problem. So often we want to know the problem first and then uh, to compute and see the results, not to compute already and see the problem. Alright, things like that. So all in all, I think this is all the important stuff. And in order to come back after I read up all this, alright, then it kind of makes sense. These are the stuff that is required: fiber type, mechanical properties. These are all things for in terms of composite. Alright, and nonetheless, you also need to know, if to go into more details, is because that page 19 to 22 covers the whole structural system. Alright, the structures meanings the matrix itself plus your fibers all along. So in our context over here now, it's talking about purely on fibers. Alright, and sh- and one thing to take note home is that the fibers will break because fibers are stiff, as we have said earlier. Alright, they are stiff. So try to ensure that the fibers won't break. Alright, and this is why the matrix is also important. The matrix itself is ductile. Okay, so I think this is all for understanding of the fibers. And next video we'll talk about using the fibers to design fabrics. Alright, so yeah.